Okay, did everybody have a good Easter weekend? Good 3-day weekend? Okay, we are down to 5 weeks of school now. Really, almost 3 when you think about it, because in 2 weeks, what's that week? Star testing, so those will be late start days, shortened classes, and then the last week is always going to be, just basically reviews and finals. So really, we got 3 weeks to go ahead and finish everything that we need to talk about. So again, don't let me forget at the end, about the last couple minutes, I just need to go ahead and very quickly talk to the IB students who are here. If you're not IB, then you don't have to worry about it. But your class average, 73.9, so it's passing. That's a good thing. So you did come in third. Okay. Do we have any questions on the test? Number 6. Okay. Number 6, it says, as a speedboat glides through the water, it creates a wake in the shape of a parabola. Okay, so basically there's my parabola right there. The vertex of this parabola meets with the stern of the boat. So we go ahead and say there's the vertex right there. A swimmer on a wakeboard attached by a piece of rope is being pulled by the boat. When he is directly behind the boat, he is positioned at the focus of the parabola. The parabola formed by the wake can be modeled by this general form, where x and y are measured in feet. So write the equation in standard form. Okay, so what we're going to have to do here is complete the square. So any term I'm not going to do that with, I want to go ahead and get rid of. Y squared plus 10y plus some number equals, if I go ahead and add 180 over, and if I subtract 565, okay, kind of ran out of a little room there. But I'm able to complete the square because the leading coefficient on the quadratic term is already a positive 1. So how do I complete the square? Okay, Susie says take that middle term, divide by 2, and square it. So what is half of 10 squared? 25. So whatever I do to one side, I'm going to go ahead and do to the other. Okay. Now this is a perfect square trinomial. I'm going to condense this to y plus 5 squared. Excuse me. All right. Equals. Now this is going to be 180x minus what? What's a negative 565 plus 25? Negative 540. Okay. And then y plus 5 squared equals, if I pull out that 180, because I need a 4p coefficient, that would be x minus 3. 180 times 3 is going to be 540. So there's the standard form of my equation. Put the 180 here, x minus 3, and then we have y plus 5 squared. Okay, and then it says, how long is the length of rope attaching the swimmer to the stern of the boat? Well, it does go ahead and say that when he's directly behind the boat, he is positioned at the focus. So if he's the focal point, all I need to do is take that 4p coefficient and divide by what? 4, okay, in order to find p. So 180 divided by 4 would give me 45 feet. Okay, so he's 45 feet behind the boat. Who asked about this one? Okay, does that make sense, sir? Okay, what else? Susie, was that your question you were asking about? Oh, okay. Okay. Number 5. That's actually been a very popular one today. So let me take this off here. Okay, so number 5, it says write an equation for the parabola in standard form. It has a focal point at negative 4, negative 4. It opens left and contains the point negative 7, 0. Well, the fact that it opens left already tells me this has to be y, that's got to be x. Okay, so let's look at this graphically for a second. I'm going to go ahead and move this back over. So it contains the point negative 4, negative 4. That's my focal point. So let's say this is my focal point right here. And it goes ahead and has the point negative 7, 0. Okay. And what we're wanting to do is write the equation. Well, in order to write the equation, I need the vertex and the what? The value of? P. Okay. Well, kind of look at the diagram we have here. We can actually use the definition of a parabola to kind of help us out. If we have this focal point right here, here's the vertex. Remember, a parabola was all the points in a plane such that the distances from that point to a fixed point we call the focal point. So let's say just some random point here. And the distance to a fixed line that we call the directrix are equivalent. Okay. All right. So any point on the parabola, if I connect it to the focal point, that is the exact same distance perpendicular to the directrix. So I could use that to my advantage here. I can go ahead and figure out what the distance between the focal point and that other point, -7, is going to be. So you could go ahead and use the distance formula, but if you look, you could create a right triangle based off that, where the base is 3, the height's what? Ooh, 4. So this is a 3, 4, 5 right triangle. So what I would want to do is go 5 units back, and that should put me at the directrix. So 1, 2, 3, 4, 5. Okay, so here's my directrix, x equals -2. Well, remember that the vertex is always going to be midway between the directrix and the focal point. So my vertex should be at what location? Looks like negative what? -3, -4. And then the distance from that vertex to the focal point is always P, and I can tell here that P is equal to 1. Okay. So my coefficient here would need to be a -4P. So this would be -4. Oh, that's the wrong one, sorry. This would be -4, and then it would be x plus 3, y plus 4. Okay. Who was it that asked me about that one? Okay, Jack. Does that make sense? Okay. Anything else? The bonus. Okay. Talk about the bonus real quick. Okay, so it says, let me get this out of the way. All right, actually, let me move this up a little bit so I don't have to keep going down so far. There we go. All right, so it says write an equation for the line tangent to x equals, excuse me, the parabola, x equals 5 minus 1/4 y squared at the point A, which is 1, -4. Okay, so the first thing I did was I tweaked that equation a little bit. I put it in the standard form that we know a parabola is going to be in. So I subtracted the 5 over. So x minus 5 is equal to -1/4 y squared. And then we know that the coefficient of the squared term has to be a +1. So I went ahead and multiplied through by -4. So -4 times x minus 5 is equal to, that would just be y squared. So I'm going to go ahead and write it as y minus 0 squared. Okay, so just a little bit of manipulation, and I was able to get the standard form. But what's the vertex? 5, 0. And I can tell that it's opening left because y is squared and we have a negative coefficient. So 1, 2, 3, 4, 5. So there's my vertex. Okay. We know it contains the point 1, -4. So 1, 2, 3, -4. That's the point we want to go ahead and create the tangent line at. Now, all parabolas are going to be symmetrical, so I could also go up 4 points, and that would give me enough to go ahead and kind of draw this thing. All right. So right here at this point, 1, -4, that's where I want to go ahead and draw the tangent line. Okay. Well, remember, we did one of these on our focus activity. What we did, the point where we're wanting to draw the tangent line, we connected that to what? Was it the vertex or the focal point? Vertex or focal point? Which one was it? Focal point. Okay. So if I'm looking at my equation here, -4p, so 4p is equal to 4. So I know p equals 1. The coordinates of the focal point should be right here at 4, 0. So if I go ahead and connect that point where I want my tangent line to the focal point, whatever that distance is, if I follow it along the axis of symmetry, where I stop should be a second point on that tangent line. Okay. So again, you could use the distance formula, but actually this one also creates what type of triangle? 3, 4, 5. Okay. So if this distance from the point I want to the focal point is 5, then this distance has to be 5 as well. So if I'm at the point 4, 0, and we move 5 units to the right, what's another point on that tangent line? 9, 0. Okay. So now I have 2 points on my tangent line. I can find the slope, and I can go ahead and write it out. So the difference of the y's, 0 minus -4 would be 4, 9 minus 1. So it has to be a slope of 1/2. Okay. And I don't remember how you guys like to do it. Did you want me to plug into point slope, or did you just want me to plug into slope intercept? What would you guys prefer? Zach, what do you think? Point slope or directly into slope intercept? Slope intercept, okay. So y equals mx plus b. So we already have the slope m. What point would you like, Zach? 9, 0 or 1, -4? 1, -4, okay. So we're going to use this point right here, 1, -4 is my xy. And see, this is going to allow me to solve for b. So -4 should equal 1/2 times 1 plus b. Okay. So -4 equals 1/2 plus b. So b is equal to -4 minus 1/2, -9/2, or -4.5. Okay. So the equation of my tangent line should be 1/2 x minus 9/2. Okay. Satish, is that good? Okay. All right. Now, I think there were several people in here who did get the bonus, correct? I was thinking so. I thought at least every class, at least some people got that. But all right, anything else? All right, if you are one of those folks who happen to score below a 70 and you're wanting to retake, you can absolutely do that this week by Friday morning, 8:05 Friday morning. Okay, because on Friday I'll be submitting progress reports, and can you believe that? We're already at the third week of the last 6 weeks. It's going to go quick, especially for the seniors. You're going to be walking across that stage pretty soon. All right, so if you do have any other questions, let me know. Let's talk about some ellipses. Okay. The only thing I have as far as this week, we're going to continue with conics. Hopefully we'll begin hyperbolas before Friday because we really need to if we're going to get everything done. So hopefully by tomorrow we should pretty much wrap up the majority of the notes. We'll kind of see how that goes. But on Thursday, remember you're having a quiz, but it's going to be over what? It's going to be over circles, okay, because I wasn't able to put that on the test. I'll go ahead and give you a circle quiz. Now, some of you may or may not have been contacted by Wesley Trook. He was not in favor last week of just taking 10 points for completing the packet. You remember we talked about that? The packet, the circles, was going to be the bonus for the quiz coming up. So he came up with an idea that I kind of liked. I'm going to go ahead and try to meet in the middle ground and see what you guys like. His idea was that if every person, now we're not doing the entire pre-cal class, we're talking about just the individual classes. Okay, so if everybody in this class brings their completed circle assignment on Thursday, shows it to me right before the quiz, everybody would get to work together. Okay. But the drawback to that was he said, okay, if some people don't go ahead and complete it, then what would happen? You wouldn't get to work together, but the people who complete the assignment would get to remove a question from the quiz that they don't like. That's the part that I wasn't really big on. So I'm willing to compromise. I'm willing to compromise. So if everybody complete, and we're not talking about accuracy, we're not going to be grading this, it's just completion. If everybody works the packet, the circle packet, shows up on Thursday, everybody has it done, I've got no problem with you guys working together on that quiz. But I'm thinking if there are some people who don't go ahead and finish the packet for whatever reason, I definitely don't want to call anybody out. I don't want to say, well, Jack is the one who caused everybody not to work together. And, I don't want to go ahead and be put in that position. So I would say if that's the case, anybody who does bring in the completed assignments, you would still just use that as your bonus. What do you guys think? Is there anybody who... Okay. Well, because it's fun, right? It's math. We've only got 5 weeks, and you want to get as much in as you can, right? Absolutely. I mean, uh, I've got no problem, like I said, with you guys working together. Is there anybody who already is thinking, there's no way I'm going to get that circles packet done by Thursday? No judgment. I'm just wanting to know. Okay. Raphael, who are you talking to? Oh, okay. You think you can get it done? Okay. So that's what we're going with. So we'll see if you guys, what happens. Okay. All right. So let's talk about some ellipses here. An ellipse is the set of all points in a plane whose distance from two fixed points that are going to be known as our foci, focal points, in the plane has a constant sum. The fixed points are the focal points. Okay, so here an ellipse is going to have two focal points, and they are going to be responsible for constructing our ellipse. So the further the focal points are from each other, the more elongated or oval-like your ellipse is going to be. So what do you think is going to happen to the graph if those focal points are much closer together? It's going to be more circular. That's exactly right. Okay. Now, the line through the foci is the focal axis. I never refer to it as the focal axis myself. I always refer to it as the major axis. You'll see all the vocabulary coming up in just a moment. But the point on the focal axis midway between the foci is the center. Okay, so the center is always midway between the focal points. The points where the ellipse intersects its axis are the vertices of the ellipse. Okay, so really the only thing I want you to pay really, really close attention to is just the first sentence here, the actual definition of an ellipse. So let me go ahead and give you some time. Here's a bunch of vocabulary, and I've got a couple of ellipses diagrammed for you. So I'll give you a couple minutes to jot that down, and then we'll go ahead and start talking about what all this means. That's And through this lesson, we're going to ultimately diagram different versions of the ellipse several times. Because knowing how it's constructed and all the vocabulary associated with it's going to make it much, much easier to work problems. Is everybody about ready? Okay, now I'm not going to read that to you word for word. I'm just going to go ahead and talk about their construction and just bring up the vocabulary as we go, because I think some things are more important than others. But, okay, basically, an ellipse is always going to have two axes, the major and the minor. Now, we're not going to be doing any rotations in here, like we talked about previously, so your major axis is always either going to be horizontal, as in the top one, or it's going to be vertical, as in the bottom one. Now, the major is going to be the more important of the two, because on the major axis, that's where you're always going to find your focal points. And the way we are looking at the definition, those focal points are going to determine what your ellipse looks like. Okay? So we have three distances here, which is a big difference from parabolas. All the distances in a parabola were based on one variable, p. Well, unfortunately, we can't say that for an ellipse. We have three distances, a, b, and c. Now, the endpoints of the major and the minor axes are where two of these distances are going to come in. Okay, the endpoints of the major axis, we call those vertices. Okay, the endpoints of the minor axis, we call those covertices. All right. And then, of course, on the major, you have your focal points that I'm just calling here F. So from the center to either vertex, it's always going to be A units, whether it's running horizontally or vertically, does not matter. A is always going to be associated with the major axis. From the center to a covertex, the endpoint of a minor axis, that's always B units. And then C will run from a center to a focal point. Okay, so how far a distance do you think it is from one vertex to the other? 2a, there you go. The major axis is always going to be 2a units long. From a covertex to a covertex, that's always going to be 2b units long, or not 2b. Little Shakespearean joke for you right there. Okay, and what's the distance from a focal point to another focal point? It's always going to be 2c. Now, I'll talk about this more in just a moment, but of all three of your distances, A is always going to be the largest distance. In fact, the relationship between them will be that B squared plus C squared equals A squared. Okay. A is always the largest distance, so it would have to represent the hypotenuse in the right triangle, and I'll go ahead and show you where this is. So let's go ahead and talk about the definition first. Okay, so here the major axis is running horizontally, okay, because the longer of the two axes that we see is, horizontal. So I'm going to go ahead and say this is the major. This one right here would be the minor. But it's the focal points that are going to determine what the ellipse itself is going to look like. Now, the definition said that it's the sum of the distances from any point on the ellipse to my two focal points. It's always going to remain constant. So what that means is, let's say I choose any point on this ellipse, like this point right here. If I connect that random point to both of my focal points, whatever these two distances are, let's call this one distance 1, let's call this one distance 2. Okay? Distance 1 plus distance 2, it's always, always, always going to add up to the exact same thing. And what you're going to find out It's 2a. Remember, what does 2a represent? That's what length? That's always the length of the major axis. Now, this will work for any other point you choose on the ellipse. If I were to go ahead and choose this point right here, okay, connected it to both of my focal points, whatever this distance is plus this distance, again, would give me 2a units. Okay, so the sum of the distances all the way around are always going to give me the length of the major axis. So I have a little bit of animation right here to kind of help you see that. Okay, so you'll notice at the bottom, the length of that segment is always remaining the same. The only thing that's going to be changing is the length of the blue line and the length of the red line. Okay, so if I were to go ahead and push play, so these guys right here are my focal points, and you'll notice as we go around these two distances, their sum is always the same. Okay, so let's do that one more time. And you'll notice, let me go ahead and pause it right here. I'll use my mouse. You'll notice the length of this line segment is the exact same length of the major axis, 2a. Okay. So does that animation kind of help you with that definition? Does anybody have any questions on that? Okay. Well, one other thing I want to go ahead and mention, okay, those two distances that you're always adding up, there are only two locations on the ellipse where those two distances will be exactly the same length. Can anybody tell me what you think they are? The co-vertices, that's exactly right. Those are the only two locations where those distances are going to be the same. So let's say I have my focal point. So let's say I connect it to this co-vertex right here. Okay, so this distance plus this distance. So I know that those two distances, when I add them up, is always 2a, right? Well, if this is one of two locations where they're the same, that would be a units. That would be a units. Now help me out from the construction, the other distances. What's the distance from a center to a co-vertex? B. From a center to a focal point? C. And look at the right triangle that's created. B and C are your legs, while A is the hypotenuse. It's one of those distances we connected to a focal point. So that's why we have the relationship that B squared plus C squared equals A squared. For an ellipse, A is always going to be the biggest distance. Okay. Any questions? Okay. Well, this next diagram here goes ahead and just talks about if your ellipse is at the center, you know, moving vertically and horizontally, A, B, and C units. Okay, that's pretty straightforward. But this table here actually tells you, you know, what items specifically you should be having if your ellipse is located at the center. Okay, so I'll give you a moment to jot that down, and then we'll kind of talk about it. So when you're talking about the distances, the major axis will always be associated with A. Okay, the minor axis will always be associated with B. And then, of course, to find C, you can use that modified version of the Pythagorean theorem to find it. But there's also a shortcut that I'll show you where you may not need to use that. there's a couple things about the equations here. You'll notice the numerators are where you're going to find your center. So anything you add or excuse me, anything you add or subtract to x and y, that becomes your h and k. Here, if it's centered at the origin, you don't have to put anything. You could put the zeros in, as we've talked about with circles and parabolas. But these are the standard form of an ellipse where the major axis is running horizontally or vertically. Now, it has to equal 1. If it doesn't equal a positive 1, well, then it's not in standard form. That has to do with what we call the eccentricity of the graph. That's something that we're going to talk about later in this week, so don't worry about that right now. But you'll notice what value, A, B, or C, did I always say was going to be the largest? A was always the largest, right? So in your equations here, whether horizontal or vertical, A squared would be larger than B squared, right? That's how you tell what direction your major axis is going to be running. If the larger denominator, A squared, is below X, then the major axis is horizontal. So you'll be going left and right A units, up and down B units. If the larger denominator A squared is below Y, well, then the major axis is going to be running vertically. So in that case, you'd be going up and down A units and right and left B. It's really similar. Once you know A and B, you're just going to go out those distances from wherever your center is located, and then you're going to go ahead and draw the actual graph. We won't be using the sum of the distances to my focal points to actually construct it, even though that's actually how they are done. All right. So let's try an example, and let's see what you guys think. So x squared over 25 plus y squared over 9 equals 1. So this can be written in this way. You could say x minus 0 squared over 25 plus y minus 0 squared over 9 is equal to 1. I mean, that's equivalent. Again, if you like to include the zeros or not, completely up to you. All right. But the first thing we want to go ahead and figure out is A, B, and C. Okay, well, my denominators are 25 and 9. The larger denominator for an ellipse will always be A squared. So I know by looking at the equation, A squared is 25, so I know A is what? 5. So I know A is 5 units long. Okay, so that means the other denominator, the smaller denominator, has to be B squared. So if B squared equals 9, then B equals 3. Okay, just like that. Now, can you tell me, is the major axis going to run horizontally or vertically for this graph? Why horizontally? There you go. The larger denominator, A squared, is below the X. Because it's below the X, I know he's running horizontally. Okay. If the larger denominator had been below Y, then the major would be running vertically. That's how you tell. All right. Well, let's go ahead and find C. Remember, the relationship was that B squared plus C squared equals A squared, right? So I'm going to go ahead and use the formula, and then I'm going to show you the shortcut, which a lot of people are probably already noticing. Well, the denominators are A squared and B squared, so we just plug them in. So 9 plus C squared equals 25. So C squared should equal, oh, now it's 16, so ultimately C will equal 4. Okay. C4, because ellipses are the bomb. That's actually pretty good, right? No, actually, I just came up with that on the spot. See, sometimes it just happens. You know, based on your reaction, I will not do that with 8th period. Everybody's like, okay. So C is 4. Okay. See, it just comes to me, my magical wit. There you go. Very quiet in here. Okay. But here's the shortcut. You can always take your denominators and go ahead and plug them into this modified version of the Pythagorean theorem. But if you realize these are A squared and B squared, and you're dealing with an ellipse, if you immediately just subtract your denominators, that will always give you C squared. So 25 minus 9, square root of that. Okay. So whatever you want to do when you're filling that out. Now, which distance is always associated with the major axis? Was it A or B? A. In fact, the length of the major axis was always 2A units long. And if A is 5, then I know the full length of this graph has to be 10. Okay. So now we just go ahead and start, plotting our points. We know the center has to be where? 0, 0 from the equation. Okay, so I'm going to go ahead and put 0, 0. Now, because the major axis is horizontal, I'm going to go left and right a unit, so 5 units. So 1, 2, 3, 4, 5 right, 1, 2, 3, 4, 5 left. Okay. And then how far up and down am I going to go? Yeah, because that's B, that's always associated with the minor axis. Okay, so I'm going to go up 3, down 3, and then just like a circle, I'm going to use those 4 points to hopefully draw something that looks like an ellipse. Okay, and not basically egg-shaped. All right. So here's also another thing I like to do. If you're going to have symmetry in these graphs, so if it works out, like here, your major vertices, the endpoints of the major are your vertices. The endpoints of the minor are your co-vertices. So here you'll notice we have 5, 0 and negative 5, 0. You could absolutely go ahead and write those as 2 separate points, but if I have the opportunity, I like to go ahead and condense those. So I write 2 points as 1 just using plus and minus. Okay, you don't have to do that. That's just something I prefer to do. Okay. So I could do the same thing with the co-vertices. Can anybody tell me what the condensed version would be? 0 what? Plus or minus 3. There you go. Now the focal points, okay, that's always C units from the center, and it's always found on what? The major or the minor axes? Focal points are always on the major. So I'm going to go horizontally with those as well. So 1, 2, 3, 4, there's a focal point. Negative 4, there's a focal point. So I can condense those as well. Plus or minus 4, 0. And there you go. And then really, I mean, there's not a whole lot of difference between an ellipse that's centered at the origin and one that's not. You'll just be moving horizontally by adding or subtracting to the x value, moving vertically by adding or subtracting to the y value, just wherever you end up at. Okay. Any questions on ellipses? How are we doing so far? Okay. Now remember, today we looked more at the construction and vocabulary, so I think once we get a few more problems done, it'll probably help people feel better. Okay, but that is as far as the other classes got, so we'll stop there. And we still got a good, like, 7 or 8 minutes left, so there you go.